Now, this is the chapter 10's rotation of a rigid object about a fixed axis. This is part 2. So from the first part, we did learn about how we calculate the angular informations, and also a part of torque that involved, right? Rather you have force exerted to the system. Now, if you introduce force not pass through the center of the mass, it can introduce some torque, and you can calculate the net torque. You can operate through the vector operations, for example, the cross product, to get the torque quantities. So now this part is more generalized, try to explain how the system rotates under these conditions. What we did learn, we look into the system as calling the particle of the system, and now we're going to move to the system of the particle, not only a single particle now, and also the rigid bodies. The rigid body is represent the body that not deformed through the force that exerts to the system. So when you have the net torque exerting into the particle, you know that the r is the distance from the rotational axis. For example, this position as the axis for rotation. If you have some force exerted to the system, so if the particle here with the mass m moving with the constant velocity or velocity with the accelerations, like this case, there's going to be some tangential force involved into this part. So the tangential force due to the change of the tangential velocity with the times, but with the velocity at tangential, the direction change introduced to the radial accelerations. And these radial accelerations, Fr equal to mv squared over r. We did learn this from the circular motions. So from this term, if you represent the change of the velocity with the time at accelerations and you multiply with the mass, you can see this force exerting to this mass with the radius r here. So r cross f or r and multiply with ma. That is the torque. So you rearrange the term because you know that the translational quantities from linear to angular, you can have s, which is the path or arc displacement, this part. S equal to theta r. Theta is the angle that sweep when this object moving. So S equal to theta r. So that V also equal to omega r, because if you dip by dt from both terms, you can get these informations. So with the acceleration is equal to alpha r. So rather than you have a as a tangential accelerations, you can rewrite it in terms of alpha r here. And with alpha r, you rearrange and you have r inside, so that you have mr squared. So the mr squared here is what you define the particle m that have distance r moving around the axis. And this is called the moment of inertia. Thinking in terms of comparisons, if you have a Newton, second law of Newton, you tell about force and mass with the accelerations. In this case, about the rotation, this is a rotation, this is translation. In terms of translation, you think about force, mass, and acceleration. But in terms of rotation, you think about torque, moment of inertia, and angular accelerations. So it's a kind of comparisons. It's quite similar, but rather than you talking about the object displaced, now object is rotate. So you have torque that's similar to the force, you have moment of inertia that's similar to mass, and you have the angular accelerations or alpha here that similar to acceleration in linear. So the definition of moment of inertia is the thing that resists any force or torque that exerts to the system to change their angular velocity or creating some angular accelerations. Those are definitions of, we can just like go through it quickly, and we have a big picture or more understanding through the example. So rather than you identify the object as a particle through the particle, like a group of the particle or a system of the particle, here we can also define the torque that happens, and this is from vector definitions that we did learn already. But if we know that all these objects are spread around and what exerted by these type of force, as you can see, these objects rotate in the same directions, or the torque that exerted to the system is have the same rotations. So in this case, I assume they are moving with the same direction, so that you can thinking about torque in terms of scalar. So this torque is come from the individual. You can write down torque like this size, also with this town, a big town or small town. This can be used for torque. And torque is vector, right? You should have had on it. But now we not consider it as a vector. We think it's as a scalar in same directions. So when they're moving in the same directions, you have each individual torque I. So you can sum up to find a net torque here. This is the net torque because you would like to sum up all individual small particle mi and sum up together. So you have a net torque here. And rather than you have mi/ri square, here you have a sigma because you would like to group up all of them. And this is the definitions of the moment of inertia of the system of the particle, not only a particle, right? Because if you look only a particle is equal to mi/ri square because only one mi. Now you sum up all, you have to add a sigma into it. This is the definition of moment of inertia. When you have the system that there are many particles, more than one particle, you can use this formula to identify the moment of inertia of the system. With that, your net torque involved here also involved with the group up of the system of moment of inertia of the system of the particle that multiply with the angular acceleration here. So these are all introductions and try to brief you about how we can derive the moment of inertia and find out in the system of the particle. And these are difference between force and torque that I already stated. Force is what you acting at the center of mass. But when torque happens, that force not directly exert to the center of mass. It goes to some point with some distance that perpendicular to the torque, the force to the axis of rotation or the center of mass that rotates. That is the torque that happens to the system. So you can have the second law from the linear definitions and second law from the angular point of view. That's quite a thing as well, because if you look into the force is unit as a newtons, but how about the torque? Torque, you can have this type of definitions, or it can be derived from R cross F, right? So F is in newtons and R is in meter. It is not directly in terms the same of definition, but you have quite surprised the same unit as a work, because work is force that dot S, right? F dot S is the work. The unit is Newton meter. Is accidentally coincidence having the same unit, but from definition they are different. You understand this point, right? Okay. From now, who mix up about the definition of unit, you can revise in the dimensional analysis sections, because we would like to identify just only the scalar properties and determine the unit. But somehow, if you look back into the definitions of vectors, you can see this is the dot products. This is a cross product, right? The definition is different, but unit is kind of similar. Okay, I move forward to the further sections. You will learn how to find all these moment of inertia of regular or geometrical objects. This is kind of like a hollow cylinder, which is you have thick with the radius r, and there's cavities or hollow at the center of it. With this one, you have the thickness here from R1 and R2. From all these, you may or may not remember. It doesn't matter. I will give you the value of moment of inertia from individual part of rotation like this in the index if you go through the midterm exams. But however, you should have some idea about difference of moment of inertia. For example, for this thin hoop is mr square. For the thick one without any hollows, you have it's equal to 1/2 mr square. And for this part, I think like I'm not suggest to remember this, but if you want, you can do it. But for the rod is 1/12 ml square, which is L is this length. And for a sphere, a solid one is 2/5 mr square. And the thin, which is you have the cavities or hollow inside, is 2/3 mr square. So all these are moment of inertia, and you can see different type of object, different axis of rotations. You have different moment of inertia. So it depends on mass, radius, and also the directions of rotations. So this rotate around z axis here. As you can see, if you saw the cylinder and it's changing the rotational axis, this is still a cylinder, but when you look from both, you can see it as a rod. So the rotation axis is matters, the mass is matter. For this problem, you're gonna use the knowledge from the net torque that equal to moment of inertia multiplied with the angular accelerations, because you would like to determine the angular acceleration here, this part of the wheel. Because what is happens if you look into this system, this mass m translate downward with some accelerations, and with tangential accelerations, it's due to the change in the velocities, right? And this acceleration led to some torque that involve, if the force which is T exert onto this pulley, there's going to be the torque which is net torque that equal to I alpha that make this pulley rotate. You would like to determine the angular acceleration of these rotations. So when you look after the first type of free body diagram here from the pulley, you got the relations from the second law of Newton's. This one is in the form of Newton's. This in the form of rotational or angular relations. with this. So this is, I note it as the first equations. How about the second ones? With this box also have some translation as well. You can see it's due to the second law of Newton's. So rather than you have torque here, you can see the force that exert to the system here is sigma F equal to ma in this case, which is the mg minus t equal to ma. With this part, you will know that the I here is related to some mass m. So since you already know that, you know that this I equal to 1 over 2 mr squared. We will note this and identify it later, but in this case from now I will put as I first. This is from the second law of Newton's in terms of the angular point of view. This is the second law of Newton's in linear point of view. So you have these two relations and try to solve the angular accelerations. From these relations, since you know that torque in this case is force with the distance. As you can see, the force is T here and the distance is this R. So the torque in this case is TR. T is the string tensions. If you look out of the pulley, the T gonna get off like this. And the torque is R cross F. So direction of the torque is pointing outward like this. This is the torque directions. But no worry about this. We gonna count as a scalar in terms of this calculation equal to I. And how about alpha? We know alpha have some the translational quantity relation from the tangential to the angular. So in this case, alpha equal to AT, which is A, I will write down. In this case, A over R. You have the first relations, and finally, you will have this A equal to TR square over I. Because we're gonna use this later, I will write down here A equal to TR square over I. This is the equations. I will not add equation 3. This is equation 3. How about this term? This term we can see some relations of the tensions and also acceleration as well. If we have acceleration, we can compare to the equation 3. So I will put everything and have A only left on the right and left hand side. So I got A equal to mg minus t over m. So now you got A in this form. So both of equation 3 and 4 are A. If I link these equation together, so because 3 is equal to 4, so you got TR square over I equal to mg minus t over m, like this. So with these relations, we can try to rearrange the terms. So finally, you're gonna get t equal to mg 1 plus mr square over I. So try to arrange this term and have t left. I will note this as my equation 5, like this. So I would like to sub this t into equation 4. So I sub 5 into 4. So what I gonna get? I gonna get the term that A equal to mg minus, and the t term is mg 1 plus mr square over I, like this, and with 1 over m. So the term ms can get rid of each other. So if you would like to determine the alpha, which is a over r, so you can have all value in and rearrange. Try to rearrange it and find out. Finally, you're gonna get alpha equal to g over r plus I over mr here. And this is in radian per second. So this is somehow you using the knowledge from the second law of Newton's in angular points of view and second law of Newton's in terms of translational. Both of them have the links of the tangential accelerations. Somehow you can redefine t from this term and sub in and rearrange this form to have the final alpha from the definition of alpha equal a over r.